Here in Chapter 9.2, we study a special type of sequence and its related sum. That sequence is known as an arithmetic sequence. So what is an arithmetic sequence anyway? A sequence is arithmetic if the difference between each consecutive term is the same. Difference meaning subtraction. The sequence a subscript 1, a subscript 2, a sub 3, a sub 4, a sub n, is arithmetic if there is a number d such that a2 minus a1 is equal to a3 minus a2 is equal to a4 minus a3, which is equal to any one of the terms minus the previous term is equal to d. The number d is the common difference of the arithmetic sequence. So this means a sequence is arithmetic if we take any one of the terms and subtract the previous term, and for every single term in the sequence, we get the exact same value. Let's take a look at an example. Determine whether the following sequence is arithmetic. If so, find the common difference. Well, again, if it's arithmetic, anytime I take the difference of one term and the previous term, I should always get the same value. Let's test that out. If I take the second term and subtract the first term, 7 minus 10, I end up with negative 3. Similarly, we can take the third term, 4, and subtract the second term. 4 minus 7 gives us negative 3 as well. We can take the fourth term and subtract the third term. 1 minus 4, that gives us negative 3. And the fifth term minus the fourth term, negative 2 minus 1 gives me negative 3. So taking any one of these terms and subtracting the previous term results in the exact same number. That number is our common difference. Yes, this is an arithmetic sequence, and the common difference, d, is equal to negative 3. Make note, it's always one term minus the previous term. The order is very, very important there. Let's try another one. 1/2, 5/4, 2, 11 over 4, 7 over 2. Again, we want to start by taking the second term and subtracting the first term. 5/4 minus 1/2. Well, if we get a common denominator here, this would be 5/4 minus 2/4, which gives us 3 over 4. Now, we take the third term, which is 2, and we subtract the second term. 2 minus 5 over 4. Well, again, getting common denominators, this would be 8 over 4 minus 5 over 4. That leaves us with 3 over 4. I can now take the fourth term and subtract the third term. 11 over 4 minus 2. 11 over 4 minus 8 over 4 gives me 3 over 4. And finally, I can take the fifth term here, 7 over 2, and subtract the fourth term. 7 over 2 minus 11 over 4. That's 14 over 4 minus 11 over 4 gives us 3 divided by 4. And notice that the difference, whenever I take one term and subtract the previous term, it doesn't matter which ones I pick, all right, for every single term in this sequence, if I take one term and subtract the previous term, we end up with 3/4. Therefore, yes, the sequence is arithmetic, and the common difference is 3 divided by 4. Now, the nth term of an arithmetic sequence has the form a subscript n is equal to dn plus c, where d is the common difference between consecutive terms of the sequence, and c is equal to a1 minus d. Every arithmetic sequence can be expressed in this form. So here, we're going to be given a few terms, and we're going to have to come up with an expression for what is known as the nth term of the arithmetic sequence. Now look at this form. A subscript n is equal to dn plus c. Arithmetic sequences have a linear format. Compare y equals mx plus b. This is slope-intercept form of an equation of a line, and our arithmetic sequence. A subscript n is equal to dn plus c. They are the exact same format, except instead of x's, our variable that we plug in for is n, and instead of getting out y's, we get out a subscript n. That means that d, The common difference between terms corresponds to the slope of the sequence. Notice D takes the place of M, and that C represents the y-intercept of the sequence, or what you would get out when evaluating a subscript 0. All right, that would be the 0th term of the sequence, what you get out when you plug in 0. Now, on occasion, an alternative recursive form is used for the nth term of an arithmetic sequence. Another format that you might see is a subscript n is equal to a1 plus n minus 1 divided by d. That being said, more often than not, we're going to end up using this linear format to begin with here. All right, if you had to guess, this format, the recursive form, actually comes from the point-slope form of an equation of a line. But let's stick to this one up here for our next examples. So let's see if we can't come up with an expression for the nth term of the given arithmetic sequence. We are told the first term of the sequence is 15 and that the common difference is equal to 4. If we are coming up with our equation for the nth term, it must follow this format if it is an arithmetic sequence. A subscript n is equal to dn plus c. And to complete this formula, this equation, we need to know what d is and we need to know what c is. The good news here is that we're actually given d already. All right, d is equal to 4. So what's remaining? We have to find c. Now remember, c represents the y-intercept of the sequence, or what you would get out when evaluating a subscript 0. I want you to think about this graphically here. Okay, here we are told that the first term is 15. This means when I plug in 1, I have to get out 15. So I would have the ordered pair 1, 15. And because we have a common difference of 4, that means every time I go 1 unit to the right, I have to go up 4 units. So my next ordered pair would be at 2, 19. Well, if c represents the y-intercept, all we actually have to do is find what the 0th term would be by going backwards in this line. Instead of going to the right 1 unit and up 4, we are going to go to the left 1 unit and down 4. And the 0th term would be right here. Notice if I subtract 4, 15 minus 4 gives me 11. All right, so you might recall the equation from the previous page. C is equal to A1 minus D. Well, if I take the first term and I subtract D, our common difference, that would be 15 minus 4 in this case. Yes, we do indeed get the 0th term, or what would be considered the y-intercept of our sequence. Okay, obviously not drawn to scale here, but hopefully you get the picture. All right, so we have C, we have D. Now all we have to do is plug them in. Here is our equation for the nth term. A subscript n is equal to 4n plus 11. We substituted in 4 for D, and we substituted in 11 for C. A subscript n is equal to 4n plus 11. And it's fairly simple to check our work. If we have found the correct expression, we should get out 15 when we plug in 1. All right, if I evaluate a subscript 1, I plug in 1, I get out 15. Well, 4 times 1 is 4, plus 11 does give me 15. That tells me that we found the expression correctly. Let's try another one here. Write an expression for the nth term of the arithmetic sequence. A1 is equal to negative 4, A5 is equal to 16. Now, in this case, we're not given the common difference. All right, so our problem-solving process is going to be a little bit different. Still, we know that our final answer should follow this format. A subscript n is equal to dn plus c. Well, let's interpret this information. A1 is equal to negative 4. That tells me that the first term in the sequence is negative 4, meaning that when we plug in 1 for n, we must get out negative 4. If I plug in 1 for n, I have to get out negative 4. Meaning, negative 4 is equal to d times 1 plus c. Interesting. All right, what about this second piece of information here? A5 is equal to 16. The fifth term in the sequence is 16. This means that when we plug in 5 for n, we must get out 16. In other words, 16 is equal to d times 5 plus c. And what we created here, fellas, is a system of equations. And the easiest way to solve this system of equations to find out what d and c are is going to be to subtract. Use elimination. Notice that when we subtract these two equations, the c's are going to subtract to 0. All right, -4 minus 16, that gives me -20. 1d minus 5d gives me -4d. Dividing both sides of the equation by -4 gives me d is equal to 5. And now I can back substitute that into either of these equations. I picked the first one here. Back substitute that value of d in. -4 equals 5 times 1 plus c. 5 times 1 is 5. Therefore, c is equal to -9. And once we have d and c, we can back substitute them into our standard form for an arithmetic sequence, giving us our final answer, a subscript n is equal to 5n minus 9. Notice we're always going to have an a sub n, that's our output, and we're always going to have an n, that's our input. All right, and we can check our work. The correct expression will verify the given information. If I plug in 1, I have to get out -4, which I do. If I plug in 5, I have to get out 16, which I do. Therefore, we have the correct answer. Let's look at a couple more examples. Write an expression for the nth term of the arithmetic sequence. We have a5 is equal to 190 and a10 is equal to 115. Again, because the sequence is arithmetic, we know it's going to follow this format. A subscript n equals dn plus c. Interpret the given information. The fifth term of the sequence is 190. This means that when we plug in 5 for n, we must get out 190. 190 equals d times 5 plus c. Notice we plugged in 5 for n, we got out 190. The 10th term in the sequence is 115. This means that when we plug in 10 for n, we must get out 115. 115 is equal to d times 10 plus c, and again, we have created a system of equations to allow us to solve for d and c. We can solve the system by subtracting, eliminating the c's. 190 minus 115, that leaves me with 75. 5d minus 10d gives me -5d. Dividing both sides by -5, we get d is equal to -15. Now that we have d, we can back substitute. I picked the second equation here. It doesn't matter which one we pick, either will work. 115 is equal to -15 times 10 plus c. -15 times 10 is -150. I add 150 to both sides, giving me c is equal to 265. And now that we have c and d, we can substitute those into our equation. A subscript n is equal to -15n plus 265. Again, an equals dn plus c, that linear format. Y equals mx plus b. And to check our work, all we have to do is verify the given information. If I plug in 5, I get out 190. And if I plug in 10, I get out 115. We are in good shape to circle our final answer. All right, last example here. Two terms of an arithmetic sequence are given. Find the missing term. So we have the third term of the sequence and the 21st term of the sequence, and we are asked to find the 100th term of the sequence. Well, if we're trying to find any of the terms, the easiest way to do it is to first find the expression for the nth term. If we have the expression for the nth term, we can find any of the terms that we want. And again, because this is an arithmetic sequence, it will have the form a subscript n equals dn plus c. Well, we know the third term of the sequence is 42. This means that when we plug in 3 for n, we must get out 42. 42 is equal to d times 3 plus c. The 21st term in the sequence is 33. This means that when we plug in 21 for n, we must get out 33. 33 is equal to d times 21 plus c. We have once again created a system of equations. We can solve using elimination and subtract our equations here. 42 minus 33, that leaves me with 9. 3d minus 21d gives me negative 18d. Notice the c's are going to subtract to 0. 9 is equal to negative 18d, which means that d is equal to negative 1/2. Now that we have d, we can back substitute into either one of these equations. I picked the first one. 42 is equal to negative 1/2 times 3 plus c. Negative 1/2 times 3 is negative 3/2. If I then add that to the other side of my equation, I end up with c is equal to 87/2. And once we have c and d, we can write our equation for the nth term. A subscript n equals negative 1/2 n plus 87/2. And now that we have our equation for the nth term, to find the 100th term, all we have to do is plug in 100 for n. Right? To evaluate a 100, we plug in 100 for n. A sub 100 is equal to negative 13/2. All right, so there you have it. Arithmetic sequences, yes, they have a linear format. Make sure you are familiar with the standard form of an arithmetic sequence. A subscript n equals dn plus c.